For the limit comparison test, you're still going to have to pick which series you want to compare to, so that part is going to be the same. But you don't have to figure out which one's bigger or smaller. We're actually going to do a limit, and we're going to analyze it that way. So we're going to say that A sub n is our original series that we're trying to analyze. And we're going to say that B sub n is the comparison series. That's the one we're going to have to pick. Now, one of the conditions for this to work is that A sub n and B sub n must be positive. Otherwise, this is not going to apply. And we're going to say that the limit as n approaches infinity of A sub n divided by B sub n equals L. L is a number. It is a finite and positive number. That's going to be significant. So we can't run this limit and get some sort of infinity or NLE situation. It has to become a finite and positive number for this to work. And what that means is not that they converge or diverge, but basically the two series are both behaving the same way. So they either both converge or they both diverge. So they're going to behave the same way. Let's look at this first one. Obviously, I'm going to go through my process. It's not geometric. Nth term, yes, this does go to 0 because the top or the bottom is growing faster. So that goes to 0. It's not telescoping. Okay, integral test. No, I'm definitely don't want to integrate that. And it's not a p-series. So now I get to my comparison test. I want to go through that process whenever I'm trying to pick these. So when I get to my comparison test, I go, well, I'm looking at the behavior, and the behavior is guided by this first term and this first term because they have the highest degree. So again, kind of like spit in the ocean, this plus 10 doesn't guide this as n goes to infinity. This doesn't guide, okay, as n goes to infinity. It's just the 4 into the 5th. So when I'm looking for my comparison series, I have to consider that. So what we're going to do is we're going to compare to B sub n, and we're going to say that B sub n is going to be equal to, and I'm going to call this n to the 4th over n to the 5th. Technically, a coefficient can't have an impact on this, right? So n to the 4th over n to the 5th, which reduces, because n to the 4th over n to the 5th, that doesn't really mean much to me, but when I reduce it, now I'm really familiar with that series. So what I'm saying is that I think this series could possibly be behaving the same way as this original series, the A sub n. This, I know, diverges because it's harmonic. Not because I did anything big, but I could say by p-series, but I can just say this series, this is the harmonic series, right? Therefore, this compares, I'm not even going to write that. I'm just going to put B sub n. I'm going to put B sub n diverges. Now, if you want to go through the p-series test, you could, but you would have to go through that justification. So because I know that the harmonic series diverges, I just have that in the back of my mind. Now I'm going to do my limit comparison part. I'm going to say, okay, the limit as n approaches infinity, and I'm going to do A sub n, which is the original series. So n to the 4th plus 10 divided by 4 n to the 5th minus n cubed plus 7 divided by B sub n, which is 1 over n. Now this is a complex fraction. I don't like it. This is not what I want to work with, so I'm going to multiply by the reciprocal. I'm going to write this as one fraction. And when I multiply by n on the top, I get n to the 5th plus 10n over 4n to the 5th minus n cubed plus 7. And now I'm going back to our very first unit, and I'm just analyzing this limit. Well, that spit in the ocean, and that spit in the ocean, and that spit in the ocean. So this limit is equal to the limit as n approaches infinity of just n to the 5th over 4n to the 5th, which equals 1/4. Now, it's really important that you state this. You have to state that this is finite and positive, because that's the condition for us to use this test. If my answer is not finite and positive, then I cannot use this. So we're going to state that, and then we're going to say therefore. And because I'm working with two series, I have to be really intentional about going back and listing my first one. Technically, you could label that as like A sub n, but since I didn't do that, I want to make sure that I label it fully. So we're going to say because this is finite and positive, that doesn't mean it converges. It just means that these are behaving the same way, because basically I had a limit, and because this limit is going to a number, their behavior has to be similar enough. This isn't going to infinity. So it has to be similar enough that they're behaving the same way. So we're going to say this must diverge, or diverges. I don't have to say must, but this must diverge by limit comparison test. Again, it's because they behave the same way. Let's look at one more. Last limit comparison. I think this one's a little bit easier to determine what I want to do, what I want to compare to. You may go through this whole process. Okay, not geometric. Okay, I'm not going to use nth term because this is 0. Telescoping, no. And then I'm going to land on P series. I'm going to be like, oh, P series, but that -2 is in my way. And you may think, okay, I'd really like to do direct comparison. Well, what are you going to compare to? Well, we'd like to compare, and I'm going to put B sub n equals, and I'm going to start at n equals 2, because if n equals 1, then that becomes 1 minus 2. And now this is negative, and that doesn't work for me. So there's a reason why that index is coming into play. So we're going to do 1 over n cubed. Well, this is a P series. So the P is equal to 3, and obviously that's greater than 1. So therefore, B sub n converges by P series test. Now, at this point, you may go, I want to do direct comparison. I'm going to go ahead and just slide down a little bit. I'm going to draw an arrow down here. That's fine. But if you do direct comparison, you're going to say, okay, n cubed minus 2 is either less than or greater than 1 over n cubed. You're going to say, well, because this is a -2, that means if I plug in a 2 here, that's going to be 8. If I plug in a 2 here, that's going to be 6. So this is always going to be larger than this because of this -2. Wait a second, this converged. So if I'm dealing with this converges, but this is bigger than that, I don't know if a series that if I'm bigger than finite, I don't know if this series converges or diverges. So the direct comparison is inconclusive. So this is a good example of why we want to have this limit comparison in our back pocket. In fact, limit comparison will work all the time. I just think sometimes direct comparison is a little bit easier, honestly. It's a little bit easier to see. So I like to teach direct comparison. So now what we want to do is we want to do our limit. So the limit as n approaches infinity. Original 1 over n cubed minus 2 over 1 over n cubed. So this is your B sub n. This is your A sub n. Write it as one fraction so you can see what's happening. Just multiply by the reciprocal. You do have spit in the ocean here. So you have the limit as n approaches infinity of n cubed over n cubed, which equals 1. Is that finite and positive? Yes, it is. Finite, check. Positive, check. Remember, those conditions are going to be extremely important. So this doesn't just confirm that it converges, it confirms that they behave the same. So because this one converges, the B sub n converged, this one is also going to converge. So we're going to say, therefore, this original series that we were staring at converges by limit comparison test. The comparison tests are really nice. We mostly use them with geometric and p-series comparisons. Limit comparison is a little bit more foolproof, but direct comparison can be a little bit quicker if we can see the greater than, less than.